this video we will cover exploiting intelligent systems using model inversion attacks. These are the topics we'll discuss.
Artificial intelligence is becoming a big part of our lives, whether we're searching the internet, reading our emails, or getting driving direction. As AI services become more personalized, they need more and more of our data. We share our private data because we expect that it is being used to improve our lives, and that our data is safe and protected. While data protections are critical, they are actually not enough to protect privacy.
One such threat is model inversion attack, which we'll explain in more detail throughout this video. Although machine learning systems don't look like typical hacker victims, there is a large variety of attacks that can be used against them. Machine learning algorithms may unintentionally reveal sensitive information because training data usually contain it. MIA is a particular example of privacy attacks. It aims to reconstruct sensitive features that were utilized during training having access to either output data or model parameters. There are two types of MIA. Black box, the adversary has access to the output data and can only query the model by sending the input data. White box, the adversary has access to the model's parameters and uses some reasoning techniques to discover features associated with a specific label. In 2015, Fredrickson proposed an MIA which was used against an image classifier that was trained on black and white face images. The face recognition classifier is expressed as function f. Its output represents a vector of probabilities of the image to belong to each of the given classes. For the model inversion, the cost function c is introduced. Its gradients are calculated starting with the candidate solution image, which is transformed at each iteration in order to minimize the cost function. In the picture on the left, you can see an image recovered using a model inversion attack, and on the right, you can see a training set image. There are various techniques and strategies that can help prevent MIA. One of the simplest ways to prevent MIA is through data sanitization, which involves removing any sensitive information from the data before using it to train an IS, ensuring that an attacker can't infer any sensitive information about the system from just the data. One caveat of this is that it may be time and computationally expensive as it requires semi-manual labor in order to guarantee full data sanitization. Adversarial training involves training the system to recognize and defend against potential attacks. A simple example of this could be the classification to detect and reject inputs that are suspected of being part of an MIA. However, this approach may be prone to false positives and false negatives. A good alternative to data sanitization that is less expensive to perform is called model augmentation. This modifies the IS and makes it tougher to infer sensitive information. Differential privacy is one popular security approach, which adds noise to the data in order to protect sensitive information, ensuring that sensitive data is not revealed in its data points. DP provides a statistical guarantee that the subject's privacy is protected by this noise addition. Another good alternative is by decentralizing the data for the training process. Secure multi-party computation is a security technique that enables various instances to jointly compute a function on their private data while keeping the data private from other instances. This is done by encrypting the data and then sharing it with other instances where necessary, to perform computations on the encrypted data in order to train a ML model without revealing personal information. Federated learning is a security technique that enables various instances to collaboratively train a ML model, while the data remains local for each instance and not shared with other instances nor with a central server. These trained local models are encrypted and sent to a central instance, which aggregates the updates to the global model, ensuring that data remains locally on each instance, while inaccessible to other instances, including the central instance, and consequently protecting data privacy. MIAs can be performed on vastly different use cases of intelligent systems. Vehicular networks are intelligent systems that rely on sensors and algorithms while communicating with each other to navigate. Attackers could retrieve sensitive information such as location and routes by analyzing its behavior. Communication improves real-time navigation, but exposes MIA attacks such as the fabrications of traffic situations. This is a newer and untraditional MIA attack as it makes use of real-time sensor information to poison the vehicles. The slides MIA is an extension of a standard MIA and was developed to exploit voice recognition systems by iteratively inverting overlapping chunks of audio samples. Experiments revealed that a standard MIA reached an accuracy of 54%, good enough to fool an automatic speaker recognition system, but sounding very unnaturally to humans. While the sliding MIA reached an accuracy of 90%, yielding improved constructions of speech samples, it still did not fool human listeners. The model inversion attack is one of the private attacks that aims to reconstruct the representation of the training data having access to model output data or to its parameters. MIA is an example of how to exploit the intelligent systems. Autonomous intelligent systems that defend against MIA using prevention techniques and strategies seem possible to develop.